What if the most dangerous place in the solar system isn't some distant alien moon, or a city-destroying asteroid lurking in the darkness? What if it's the world right next door, the one we once called our sister? For millennia it has been a beacon in our skies, a diamond of impossible brilliance hanging in the twilight. Before we knew it as a planet, we knew it as a promise, the morning star heralding the dawn, the evening star standing sentinel as night fell. We gave it the name of a goddess Venus, a symbol of beauty, love and light. And for centuries that name seemed to fit perfectly. Through the fledgling telescopes of early astronomers, it presented itself as a featureless serene orb, wrapped in an unbroken blanket of pale yellow clouds. It was a world of exquisite mystery, slightly smaller than Earth, formed from the same primordial stardust, and orbiting just a little closer to the life-giving warmth of the sun. It was for all intents and purposes our twin, a second Earth patiently waiting to be discovered. This tantalizing possibility ignited the human imagination. We dreamt of what lay beneath that permanent veil of cloud. Science fiction writers of the last century painted visions of a warm tropical paradise, a humid world of vast steaming jungles and planet-wide oceans. They imagined strange exotic flora, and perhaps even the first extraterrestrial life we might encounter. We envisioned a younger Earth, a prehistoric realm caught in a perpetual Carboniferous period, a world brimming with the raw, untamed potential for life. Our probes, our ambitions, our very hopes for companionship in the cosmos were first directed at this our celestial sibling. We sent our first emissaries to another planet, not to Mars, but to Venus, convinced we were about to unveil a mirror of our own lush world. The allure was simply irresistible. But the universe rarely delivers on our expectations. Often it presents us with something far more complex, far more challenging, and in this case, far more terrifying. Because the beautiful, serene vision of Venus, the gentle goddess in our sky, is a profound and devastating illusion. It is a cosmic masquerade. Our sister planet is not a paradise. It is a portrait of hell itself. The first clues came not as images, but as grim clinical data streams from those first robotic explorers. The Soviet Venera probes built like deep-sea submersibles were our first attempts to pierce the veil. Most were silenced before they could even report back. Crushed, melted, vaporized. The few that survived their descent for mere minutes sent back tidings from another reality, a reality our science could barely comprehend. Let us pull back that beautiful golden curtain of cloud. What we once imagined as water vapour is in fact a thick globe-spanning haze of concentrated sulfuric acid, a corrosive poison that would dissolve metal and flesh with equal indifference. These are not the gentle life-giving clouds of Earth. They are a perpetual chemical storm obscuring a truth more extreme than our darkest fears. Descend through them, and you enter an atmosphere that is less like a gas and more like a fluid. The pressure builds with terrifying speed, a physical weight that feels like a solid presence. On the surface of Venus, the atmospheric pressure is over 90 times that of Earth at sea level. To stand there would be the equivalent of being nearly a kilometre deep in one of our own oceans, an impossible bone-shattering force exerted on every square inch of your body. The air itself, a suffocating blanket of carbon dioxide, becomes a tangible crushing sea. It's an atmospheric vice designed to obliterate anything that dares to enter it. And then there is the heat, a heat born from the most catastrophic climate collapse imaginable. Venus is the victim of a runaway greenhouse effect, a planetary fever that never broke. That thick carbon dioxide atmosphere has trapped the sun's energy for billions of years, creating a thermal prison from which there is no escape. The surface simmers at an average of over 460 degrees Celsius, or 860 degrees Fahrenheit. It is hotter than the planet Mercury despite being tens of millions of kilometers farther from the sun. It is a world hot enough to melt lead, zinc and tin into shimmering pools on the ground. A planetary kiln where the very rocks glow with a dull cherry-red heat in the eternal twilight. There are no oceans, there is no water, there is no relief. Any drop of water that ever existed on its surface boiled away eons ago, its molecules ripped apart by solar radiation and lost to space forever. Venus is a planet that has been sterilized by its own sky. When we finally managed to map its surface using radar penetrating the opaque clouds, The last vestiges of our tropical dreams were scorched away. We found a world paved in volcanic rock. Vast basaltic plains stretch for thousands of kilometres, punctuated by immense shield volcanoes and strange pancake-like domes of hardened lava. The landscape is a twisted, tortured geography of past and perhaps present eruptions, a testament to a violent inner life that has resurfaced the entire planet multiple times. It is a young surface geologically speaking, but it looks ancient and desolate. A monolithic volcanic wasteland utterly hostile to life as we know it. This is not our twin. It is our polar opposite. A cautionary tale written in stone and fire across an entire world. Yet for all its horrors, the pressure and the heat are merely symptoms of a deeper, more fundamental strangeness. They are the result of a planet where the most basic rules of planetary motion have been broken. A world that is quite literally turned on its head. Think of our solar system. It was born from a vast spinning cloud of gas and dust. That primordial rotation imparted a foundational momentum to everything that formed within it. The sun spins, and nearly every planet from Mercury to Neptune spins in the same direction, counterclockwise, if viewed from above the sun's north pole. They orbit the sun in that same direction. It is the shared cosmic inheritance of our celestial family, a dance choreographed by gravity and time. All planets follow this rule, except for Venus. Venus spins backwards. It rotates clockwise, a slow, deliberate rebellion against the rest of the solar system. This is known as retrograde rotation. If you could somehow survive on its surface, you would see the sun rise in the west and set in the east. It is a profound violation of the natural order, a clue that sometime in its deep past something catastrophic and transformative must have occurred. What could possess the power to take a planet-sized gyroscope spinning with the force of its own creation, and not only stop it but reverse it entirely? Was it a titanic collision with another protoplanet in the chaotic youth of the solar system, an impact so violent it literally knocked the world upside down, or was it a more subtle, drawn-out process, a gravitational tug-of-war between its own thick atmosphere, the nearby sun and other planets, a delicate dance of tidal forces that slowly bled away its original momentum and sent it spinning the other way? This backward rotation is one of the greatest unsolved mysteries in planetary science. It tells us that the history of Venus is hiding a secret, a moment of profound violence or strange physics that forever set it apart from its sister Earth. The consequences of this backward spin are as bizarre as the phenomenon itself. Venus rotates on its axis with excruciating slowness. A single Venusian day from one sunrise to the next lasts for 243 Earth days. But its journey around the Sun, its year, only takes 225 Earth days. This is the only planet in our solar system where a day is longer than a year. Imagine that. The Sun would hang nearly motionless in the sky for months at a time, baking the landscape under its relentless glare. Then a sunset that would last for weeks, followed by a night that would stretch for an entire season. Time itself would move differently on this world. The rhythm of day and night so fundamental to life on Earth is absent here. Instead, there is only an endless scorching afternoon, or an equally long, suffocating night. This slow reversed spin has created a planet of profound extremes, a world fundamentally disconnected from the familiar cycles that govern our own. But the mystery only deepens when you look back up at the sky. While the solid planet beneath creeps along at a walking pace, its atmosphere is a completely different story. The upper clouds of Venus are in a state of perpetual planet-wide hurricane. They whip around the globe at speeds exceeding 360 kilometers per hour, circling the entire planet in just 4 Earth days. This is the superrotation, a vast atmospheric river moving more than 60 times faster than the spin of the world below it. Imagine standing on a carousel that takes an entire year to make one turn, while a tempest rages 60 times faster just above your head. What colossal engine drives this atmospheric machine? Where does the energy come from to maintain a global storm that never ever ceases? It is a paradox that defies our models of meteorology. A planet that is almost perfectly still on the ground, yet hosts the most violent and sustained winds in the entire solar system. Within this atmospheric chaos, we have detected colossal bolts of lightning not from water clouds, but perhaps generated by the friction of sulfuric acid droplets. We have seen enormous stationary waves in the upper atmosphere, gravity waves that remain fixed in place above specific mountains on the surface, like ethereal banners stretching for thousands of kilometers against the super-rotating flow. We have seen strange unexplained absorbers of ultraviolet light in the clouds, mysterious dark patches that consume half of the solar energy reaching the planet, whose chemical identity remains a complete puzzle. Some have even speculated against all odds that these patches could be evidence of microbial life floating in the slightly more temperate upper layers of the atmosphere using sulfur compounds for energy in a way we can barely imagine. The sky of Venus is not a static shroud. It is a dynamic, electrically charged and deeply enigmatic entity. It is the key not only to the planet's extreme climate, but perhaps to its deepest secrets. And that is why we must understand this place. Venus is more than just a scientific curiosity. It is a mirror showing us a dark reflection of a path not taken, or perhaps a path that still lies ahead. This world, so similar to our own in size and composition, is the most powerful cautionary tale in the solar system. It is the ultimate laboratory for studying the greenhouse effect, for understanding the tipping points in a planet's climate when things go catastrophically wrong. What happened to Venus? Did it once have oceans? Could it once have harboured life? And what precise sequence of events transformed it from a potential second Earth into a lethal furnace? The answers to these questions are not just academic. They are critical for understanding the long-term stability of our own atmosphere, for safeguarding the delicate climatic balance that makes our world a habitable oasis. In the searing heat and crushing pressures of Venus, we can read the physics of planetary survival, and we can learn with chilling clarity what is at stake here on Earth. It forces us to confront an unsettling question. Is habitability a permanent feature of a planet, or is it a fleeting, precious moment in time? To find the truth, we must peel back the layers of time itself. We must journey back 4.5 billion years to the violent dawn of the solar system, a time when two nascent worlds, Earth and Venus, were born as twins from the same swirling nebula. They started with nearly the same ingredients at nearly the same time in nearly the same place. Yet one became a cradle for life, a world of blue oceans and white clouds. The other became a monster. Somewhere in the deep past a choice was made. A path diverged, an understanding that single pivotal divergence in the road is the quest we now embark upon. The story of Venus is not just the story of a distant planet, it is the story of us. It's a story of how a paradise can be lost. What is it that separates a twin from a mirror image? One is a copy, a familiar echo of the self. The other is a reflection reversed and profoundly alien. For as long as we have had eyes to see and minds to wonder, we have gazed upon Venus, believing we saw a sister world. A cosmic twin born from the same stellar nursery, shrouded in a tantalizing blanket of clouds that promised a world much like our own, perhaps even lusher, more alive. But we were not looking at a sibling. We were staring into a celestial mirror, and the image it would eventually reflect back at us would be a terrifying inversion of everything we held dear. A paradise turned inside out. Before it had a name, it was a presence. A beacon of impossible brilliance, it was the first point of light to pierce the fading blue of dusk, and the very last to surrender to the encroaching dawn. For millennia it graced our twilight hours, a pearly phantom so bright it could cast a faint shadow on a moonless night. It was a celestial chameleon, a constant yet ever-changing guidepost. To the ancient Babylonians it was Ishtar, the goddess of love and war, her dual nature perfectly captured by this two-faced star that was both the herald of the morning and the sentinel of evening. The Maya masters of celestial mechanics built entire observatories aligned to its path, their calendars intricately woven with its grand 584-day cycle, a rhythm of appearance and disappearance that dictated times of sacred ritual and conflict. They tracked its every movement with a precision that bordered on obsession, seeing in its journey not just a planet, but the physical manifestation of their most powerful deities. To the Greeks it was two separate bodies, two distinct gods. Phosphorus, the light bringer, who ran ahead of the morning sun, and Hesperus, the sombre son of twilight, who followed it down into the underworld. It took the mind of Pythagoras to finally divine the truth to realize these were not two celestial beings, but one object playing two different roles in our sky, a single actor on a cosmic stage. The Romans would cement its identity, bestowing upon it the name that has echoed through history, Venus, the goddess of beauty, love and desire. And how fitting it seemed. No other object in the night sky save the moon itself possessed such a serene and gentle beauty. Its light wasn't the sharp, frantic twinkle of a distant star, but a steady, creamy, unwavering glow. It was a lamp lit in the halls of heaven, a promise of constancy in a universe that was otherwise in perpetual chaotic flux. This single point of light was a source of profound comfort, a cosmic anchor for sailors navigating vast featureless oceans and for philosophers navigating the equally vast oceans of thought. It spoke not of fire and violence, but of tranquility and hope. When Galileo Galilei first turned his new telescope toward that light in 1610, he shattered a universe. He wasn't looking for a new world, he was looking for proof, and Venus provided it in spectacular fashion. He saw not a simple point of light, but a tiny, perfect disk. And as he watched night after patient night, that disk did something that for a geocentric universe was utterly impossible. It went through phases just like our moon, a slender crescent growing to a half disk, then a gibbous shape, a glorious cycle that could only mean one thing: Venus did not orbit the Earth. It orbited the Sun. In that moment our planet was dethroned, cast out from the centre of creation, and a new, more elegant cosmos was born. Yet this revolutionary discovery came with a deep and abiding frustration. For as magnificent as the phases were, the surface of Venus itself remained a total, complete mystery. The planet that had just reshaped our understanding of the universe refused to show us its face. It was cloaked impenetrably in a uniform, featureless shroud of brilliant white. Galileo saw no continents, no oceans, no mountains, no craters, just the clouds. For the next 3 centuries, this would be the torment of astronomers. Generation after generation, they would turn ever larger, ever more powerful telescopes toward our sister planet, hoping to glimpse a break in that celestial veil, a fleeting view of the world beneath. They saw nothing. The great observer Giovanni Cassini, who charted the bands and storms of Jupiter, reported seeing faint ghostly markings, but they were elusive, refusing to hold a consistent shape. William Herschel, the discoverer of Uranus, stared for hours on end, concluding the markings were mere illusions, tricks of the eye, or disturbances in Earth's own atmosphere. The planet was a perfect polished sphere of white, a cosmic enigma that invited speculation precisely because it offered no facts. And into that void of knowledge, into that vast empty canvas, humanity began to paint its most vivid and optimistic dreams. If we could not see, then we could imagine, and we imagined a paradise. The logic seemed so simple, so compelling. Venus is closer to the Sun than Earth, so it must be warmer. Those thick planet-girdling clouds must be composed of water vapour, trapping the warmth and creating a global greenhouse. What does one get from constant warmth and abundant moisture? You get a jungle, a swamp, a world teeming with life. The idea took root not just in the fertile soil of fiction, but in the minds of respected scientists. The Nobel laureate Svante Arrhenius, a pioneer in climate science, envisioned a Venus drenched in perpetual rain, a humid world of steaming lowlands and vast shallow seas. He described a planet in a state much like Earth's own Carboniferous period, a time when our world was covered in immense fern forests and giant insects thrived in the oxygen-rich air. This wasn't just a fantasy, it was a scientifically plausible hypothesis, an extrapolation based on the only data points we had: its size, its proximity to the Sun, and those ever-present clouds. Our sister world, we dreamed, was a younger Earth, a vibrant primordial Eden waiting for us just across the interplanetary dark. Science fiction writers seized upon this vision, populating its misty jungles with exotic creatures, strange flora, and even sentient beings. Venus became the quintessential destination for cosmic adventurers, a world of mystery and untamed wilderness. We imagined the sound of constant warm rain drumming on the leaves of colossal plants, the sight of thick mists parting to reveal bubbling swamps and bizarre alien landscapes. The pure white of its clouds seemed to symbolize innocence, a world untouched by the industry and strife that was beginning to scar the face of our own planet. It was a tantalizing vision, a second chance for life to flourish, a confirmation that we were not alone. This dream of a water world, a jungle planet, became so deeply ingrained in our collective consciousness that it felt like an established truth. It was the Venus we expected to find. It was the Venus we wanted to find. But even as this romantic vision of a swampy paradise flourished, a subtle but persistent astronomical puzzle began to emerge, a problem so fundamental it threatened to unravel everything we thought we knew. The question was simple. How long is a day on Venus for Earth, Mars and Jupiter? The answer was easy. You watch the planet rotate. You pick a feature, a mountain, a crater, a giant storm, and you time how long it takes for that feature to return to the same position. Jupiter's great red spot reveals a day less than 10 hours long. The dark plains of Mars march across its face in just over 24 hours. But Venus had no features. There was nothing to track, nothing to time. Astronomers were forced to hunt for those same faint ephemeral markings that had frustrated Cassini and Herschel centuries before. These were not true surface features, but subtle shadings in the upper cloud deck, whisper-thin variations in brightness that were maddeningly difficult to confirm and track. The results were a mess, a chaotic jumble of conflicting observations. Some of the most respected observers of the 19th and early 20th centuries claimed to have timed the rotation. Many, including the famed Italian astronomer Giovanni Schiaparelli, concluded that Venus was tidally locked to the Sun just as the Moon is to Earth. This meant one side of the planet would be trapped in eternal scorching day, while the other would be frozen in an endless abyssal night. A day on Venus in this model would be the same length as its year, 225 Earth days. This theory painted a far grimmer picture than the jungle paradise, a world of extreme contrasts, with perhaps only a thin sliver of twilight, a terminator zone, where life might tenuously cling to existence. But other astronomers vehemently disagreed. They reported seeing cloud patterns that suggested a much faster spin, something closer to Earth's own 24-hour day. This would make the jungle world hypothesis much more plausible, distributing the sun's heat more evenly around the planet. For decades, the debate raged. Was Venus a slow rotator or a fast one? A world of fire and ice or a temperate, humid greenhouse? The planet's true nature was held hostage by those inscrutable clouds. The visual evidence was simply too poor, too contradictory to settle the matter. The mystery of its day became one of the great unsolved problems of planetary science. It was a fundamental property of our nearest planetary neighbour, and yet it remained completely beyond our grasp. The solution would not come from looking, but from listening. It would come from a revolutionary new form of astronomy, one that didn't rely on the feeble visible light that the clouds so effortlessly blocked. It was the dawn of the age of radar. In the early 1960s, humanity gained a new sense. Giant radio telescopes like the Goldstone Observatory in California's Mojave Desert and the Arecibo Observatory, nestled in the hills of Puerto Rico, allowed us to reach out and touch other worlds in a way we never had before. The process was in principle straightforward. You fire a powerful beam of radio waves at Venus. You wait for that signal to travel millions of miles, bounce off the planet's surface, and then travel all the way back to Earth. The clouds, which are opaque to light, are transparent to radar. For the first time, we were about to pierce the veil. The primary goal was to get a more accurate measurement of the distance to Venus to refine our map of the solar system. But the returning echo contained a secret, a piece of information encoded in the very fabric of the radio waves themselves. It carried the signature of the planet's rotation. The principle is known as the Doppler effect. It's the same reason an ambulance siren sounds higher in pitch as it approaches you and lower as it moves away. The motion of the source stretches or compresses the waves. As Venus spins, one side or limb of the planet is rotating towards us while the other is rotating away. The radio waves bouncing off the approaching limb should be compressed, shifted to a slightly higher frequency. Those bouncing off the receding limb should be stretched, shifted lower. By measuring this tiny frequency spread in the return signal, scientists could calculate the speed of the planet's rotation with exquisite precision. It was the perfect experiment, a brute force method to finally put the century-long debate to rest. The first results began to trickle in during 1961 and 1962. The teams of scientists analysed the faint echo that returned from across the void. They measured the spread of the frequencies. And they found something that was not just strange, it was impossible. The data was clear, unambiguous, and utterly profoundly wrong. The initial calculations showed a day on Venus that was extraordinarily long, around 243 Earth days, even longer than its year. The slow rotation camp had been right all along, but that was not the part that sent a shockwave through the scientific community. It was the direction. The Doppler shift was inverted. The side of the planet that should have been moving towards Earth according to the established spin of the solar system was moving away. The side that should have been moving away was moving towards us. The scientists checked their equipment. They recalibrated their instruments. They ran the calculations again and again and again. There was no error. There was no malfunction. The data was screaming a single, unbelievable truth. Every other major planet in our solar system, from Mercury to Neptune, spins on its axis in the same direction it orbits the Sun, counterclockwise as viewed from above the Sun's north pole. This shared motion is a deep memory of the swirling cloud of gas and dust from which we were all born, the primordial angular momentum of the solar nebula. It is the fundamental foundational rule of our cosmic family, but not Venus. Venus spins backwards. Slowly, languidly, defiantly it rotates clockwise. A day on Venus not only lasts longer than its year, but the sun rises in the west and sets in the east. It is a planet spinning in reverse, a retrograde world. This single discovery was a cataclysm. It shattered our neat and tidy models of planetary formation. How could one planet, our supposed twin, end up so fundamentally backward? What cataclysmic event in its deep past could have been powerful enough to not just halt its original spin, but to completely reverse it? Was it a colossal impact from a rogue protoplanet in the chaotic youth of the solar system? Or was it something more subtle, a slow grinding war waged over billions of years between the gravitational pull of the sun and the planet's own thick, heavy atmosphere? The dream of a gentle jungle world began to evaporate in the face of this first hard, anomalous fact. This bizarre retrograde rotation was the first hint that the world beneath the clouds was not a paradise. It was a place where the fundamental rules had been broken. It was a crime scene. And if a planet could spin backwards, what other horrors, what other unimaginable extremes might be waiting for us beneath that beautiful, deceitful sulfuric veil? The age of dreaming about Venus was over. The age of discovery and of terror was about to begin, and so with our telescopes rendered blind by that eternal pearlescent shroud, we had no choice. We had to go there. We had to reach out and touch the ghost in our sky to send our emissaries of wire and steel into the unknown, armed with little more than mathematics and a burning, desperate curiosity. The dream of a sister world, a lush paradise teeming with possibilities, was too powerful to resist. Humanity, newly unbound from the surly bonds of Earth, aimed its rockets and its hopes at the morning star ready to greet our long-lost twin. The first of these robotic explorers was a marvel of the atomic age, a creature of gold foil and gleaming antennae named Mariner 2. Launched by the United States in 1962, it was not designed to land nor even to orbit. Its destiny was far more ephemeral, a fleeting rendezvous, a single high-speed pass to say, a quick hello. As Mariner 2 sliced through the interplanetary void, its instruments were silent, waiting. For months it coasted through the cold vacuum, a tiny spark of human ambition, against the infinite black. Its target, Venus, grew from a pinpoint of light into a dazzling featureless orb, its clouds swirling with a serene, almost placid beauty. But as the probe drew closer, its microwave and infrared radiometers began to stir, tasting the planet's thermal energy for the very first time. Back on Earth, in the pristine control rooms of the Jet Propulsion Laboratory, scientists held their breath. They were expecting warmth, perhaps the balmy heat of a tropical Earth. The mathematics, the prevailing theories all pointed to a temperate world slumbering beneath the clouds. The data began to stream in a torrent of numbers translated from faint radio whispers sent across a chasm of 58 million kilometers, and then confusion, followed by disbelief. The numbers were wrong, they had to be. The instruments were telling them that the surface of Venus, the ground hidden beneath those beautiful enigmatic clouds, was not warm. It was hot. Impossibly, unimaginably hot. Not 80 degrees, not 100, but over 400 degrees Celsius. Hot enough to melt lead. Hot enough to turn any imagined oceans into vapor in an instant. It was a fever reading for an entire planet. The dream of a jungle world of warm seas and gentle rains evaporated in a flash of static. This wasn't a sister. This was a monster wearing a beautiful mask. Mariner 2's brief flyby was a profound shock, a jarring first draft of a horror story we were only just beginning to read. The encounter lasted a mere 42 minutes, a cosmic blink before the probe was flung back out into the darkness of the solar system, its mission complete. It had asked the first question, and the answer had changed everything. Venus was no paradise. But the why remained a suffocating mystery locked away beneath that impenetrable cloud deck, a puzzle that a single flyby could never solve. The challenge had been thrown down and another rival superpower was ready to pick it up. The Soviet Union, locked in a fierce ideological and technological struggle with the West, saw Venus not just as a scientific target but as a prize. They would not be content to simply fly past. They would conquer it. They would be the first to touch its soil. They began an audacious, relentless campaign known as the Venera program, a series of missions that would become one of the most heroic and heartbreaking sagas in the history of exploration. The first attempts were brutal lessons in the unforgiving nature of space. Venera 1, launched in 1961, fell silent long before it even reached its destination, a ghost in the solar wind. Venera 2 suffered the same fate, its systems overheating as it flew past the planet, a mute witness. Venera 3 was designed to be the first to strike the surface, but it too lost contact, becoming the first human-made object to impact another world, though it delivered its message of arrival in utter silence. For years, Venus was a spacecraft graveyard, a siren of the solar system luring our best efforts to their doom. These Soviets were learning a terrifying truth: the space around Venus was just as hostile as the planet itself. But they were unyielding. With each failure, they returned to the drawing board, building tougher, more resilient machines. They reinforced the electronics, strengthened the communications, and armoured their probes for a battle against an unknown enemy. In 1967, they launched Venera 4. This was not a flyby probe, nor a simple impactor. This was a sophisticated atmospheric probe, a spherical capsule designed to detach from its parent craft and descend through the clouds on a parachute, tasting the air, measuring the pressure, taking the temperature, broadcasting its findings all the way down. It was our first true descent into the belly of the beast. We watched metaphorically through its radio signals as it plunged into the upper atmosphere. The craft survived the fiery entry, its heat shield glowing like a man-made meteor. The parachute deployed, the descent began, and for the first time humanity was inside the clouds of Venus. The initial data was electrifying. The probe's instruments revealed an atmosphere almost entirely composed of carbon dioxide, a suffocating blanket of gas that immediately explained the lack of oxygen so vital for life as we knew it. But as it descended deeper, the numbers streaming back to Earth grew more and more alarming. The temperature climbed relentlessly, confirming Mariner's shocking discovery, and a new monster emerged from the data pressure. The atmospheric pressure was rising at an astonishing rate, far beyond anything the engineers had anticipated. The probe sank deeper and deeper into the thick, soupy air, reporting pressures that climbed to 10, then 15, then 20 times that of Earth's at sea level. The controllers in the Soviet Union could only listen as their creation was squeezed by the weight of an entire world sky. Then, at an altitude of about 25 kilometers, the transmissions abruptly ceased. Silence. Venera 4 had been destroyed. It hadn't been burned up. It had been crushed, imploded like a submarine in the deepest ocean trench, its resilient metal shell crumpled by a force it was never built to withstand. The idyllic vision of Venus was not just dead. It had been pulverized. The Soviets now understood. They weren't just fighting heat. They were fighting the sheer brute force of the planet itself. The missions that followed Venera 5 and 6 were built stronger, reinforced to survive the titanic pressures. They too descended into the incandescent murk, and they confirmed Venera 4's data, before they too were inevitably crushed by the ever-increasing weight of the atmosphere above them. They had pushed the boundary deeper, but still had not reached the ground. It became a national obsession. They had to reach the surface. For Venera 7, Soviet engineers built a machine that was less a scientific instrument and more a deep space cannonball. It was a titan of titanium designed with one singular, desperate goal: to survive the descent and transmit even for a single second from the surface of Venus. Most of the scientific instruments were stripped out, replaced with structural reinforcement. The probe was a brute, an armoured fist designed to punch its way through hell. In December of 1970, it began its final plunge. It jettisoned its carrier spacecraft and blazed into the atmosphere, a screaming spear of metal. The parachute deployed, but the descent was agonizingly slow through the thick molasses-like air. For 35 excruciating minutes it fell, the temperature soaring, the pressure building to unimaginable levels. The mission hung by a thread. The parachute may have failed partway down, sending the lander into a faster, more violent descent. But somehow, against all odds, it hit the ground, and it survived. The signal that reached Earth was weak, a faint, almost imperceptible whisper against the cosmic noise, but it was there. For 23 minutes, Venera 7 transmitted from the surface of Venus, a voice from another world. The data it sent back was stark and horrifying. The temperature at the landing site was a staggering 475 degrees Celsius. The pressure was 92 times that of Earth. This was not a planet. This was a pressure cooker, an autoclave on a planetary scale. It was a place so utterly alien, so completely hostile, that it defied every romantic notion we had ever held. We had finally touched Venus, and it had seared us. Yet even this monumental achievement was not the end of the story. The Soviets, emboldened by their success, aimed for something even more audacious. They wanted to see it. They wanted a picture from the surface of hell. This required a level of engineering that bordered on the miraculous. Venera 9 and Venera 10, launched in 1975, were not just landers, they were robotic photographers. They carried cameras protected behind thick quartz windows, refrigeration units working frantically to keep the electronics from melting, and powerful lamps to illuminate a world perpetually shrouded in gloom. Imagine the scene in the Soviet control center. After a journey of millions of miles, after a descent that destroyed all its predecessors, a machine built by human hands was resting on the surface of another world about to open its eyes. The data began to stream back. Not just numbers, but scan lines. An image being painted one line at a time transmitted across the solar system. Slowly, painstakingly, a picture began to emerge from the static. It was grainy. It was distorted by the thick atmosphere. The lens cap, which was supposed to be jettisoned, was still partially in view on Venera 9's camera. But it was undeniably a landscape. There were no jungles, no oceans, no signs of life. Just a desolate fractured plain of sharp-edged slab-like rocks, stretching to a hazy, oppressive horizon. The sky was not blue, but a sickly, sulphurous yellow-orange, the light filtering down, as if through a slab of murky amber. It was a photograph of the end of the world. It was profoundly, deeply unnerving. This was the true face of our twin, a landscape baked, crushed and sterilized beyond recognition. For the first time we could truly feel the weight and the heat of this place. We were no longer interpreting data, we were bearing witness. While the Soviets were conquering the surface, the Americans returned with a new strategy. They launched the Pioneer Venus mission in 1978, an ambitious two-pronged attack designed to understand the planet as a complete system. It consisted of an orbiter, destined to study the planet from above for years, and a multi-probe bus which would release 4 separate probes to descend into the atmosphere at different locations simultaneously. The Pioneer orbiter was our first long-term eye in the sky. As it settled into orbit, it began to use a powerful new tool radar. For the first time, we could systematically peel back the clouds and map the entire globe. The ghostly radar images revealed a world of immense volcanic plains, continent-sized highlands named Ishtar and Aphrodite Terra, and towering volcanoes larger than any on Earth. It was a geologically complex world, but one without the familiar signs of plate tectonics that shape our own planet. It seemed frozen in a more primordial volcanic state. But the orbiter's most crucial discoveries came from studying the clouds themselves. By analysing the light they reflected and the particles within them, scientists made a chilling discovery that explained the corrosive nature of Venus's atmosphere. The clouds were not made of water vapour. They were composed of droplets of concentrated sulfuric acid. The beautiful pearly veil we admired from Earth was a mist of battery acid stretching for kilometres in every direction. Any rain that fell from these clouds would not be water, but a shower of vitriol that would dissolve metal and stone, a downpour of pure poison that evaporated in the intense heat long before it ever reached the ground. As the orbiter watched from above, the 4 multiprobe probes plunged into the atmosphere below. Like a coordinated scientific assault, they sampled the atmosphere from the equator to the poles, confirming the crushing pressures and searing heat were not localized phenomenon, but a truly global condition. They painted a picture of a planet caught in a terrifying, self-perpetuating trap. The pieces of the puzzle gathered at such immense cost by both nations were finally coming together. You have an atmosphere made almost entirely of carbon dioxide, a supremely efficient greenhouse gas. You have thick planet-encircling clouds of sulfuric acid that trap heat even more effectively. This combination creates a thermal prison from which there is no escape. Sunlight comes in, warms the ground, and the resulting heat tries to radiate back out into space. But it can't. It is absorbed by the carbon dioxide and the acid clouds, and redirected back down to the surface, raising the temperature even further. More heat releases more gas from the rocks, thickening the atmosphere, which in turn traps even more heat. It is a vicious positive feedback loop, a planetary thermostat stuck in the on position, with the dial turned all the way up. We had discovered the runaway greenhouse effect. This was the mechanism. This was the killer. Venus wasn't just hot because it was closer to the Sun, it was hot because its own atmosphere had betrayed it, cooking the planet alive over billions of years until it became the infernal cauldron we see today. The idyllic vision of our sister world was now a ghost, replaced by the stark, terrifying reality of a planet that had taken a different path. It was a warning etched in fire and pressure across an entire world. Our twin was not a reflection of our vibrant present, but perhaps a glimpse of a terrible possible future, a cautionary tale on a scale we had never before imagined. We had set out to find a paradise, a second Eden. Instead, we found a monument to planetary death, a world that serves as a constant silent reminder of how fragile a planetary climate can be, and how catastrophically it can all go wrong. The veil had been lifted, not revealing a face but a skull. And the most unsettling question of all began to form in the minds of scientists looking back at our own beautiful blue world. Could it happen here? And so we stand before the great celestial paradox. For every world we have studied, from the swift flight of Mercury to the lumbering journey of Neptune, in the cold outer dark a fundamental rule has held true, a kind of cosmic birthright. They spin in the same direction that they orbit our star, a shared legacy of the great swirling protoplanetary disk from which they were all born billions of years ago. They move with prograde rotation, a universal family trait, all except one. Venus, our shrouded twin, turns its back on this cosmic law. It rotates in reverse. If you could somehow endure the crushing, searing pressures on its surface, you would witness a spectacle that defies all earthly intuition. The sun would not rise in the east. It would heave itself over the western horizon, a dim, diffuse glow filtering through that suffocating yellow sky. And it would move with an almost imperceptible slowness. A funereal pace across the heavens for a single day on Venus lasts longer than its entire year. Imagine that. Imagine a planet where the day outlasts the year, a world where time itself seems to run backwards. This is not merely a planetary quirk. It is a profound violation, a ghost in the solar system's machine. It suggests a history written not in the quiet accumulation of dust and gas, but in a language of immense violence, or unimaginably slow grinding forces. To understand Venus, we must confront this central defiant act. We must ask the question that has haunted planetary scientists for decades: what could possibly have happened to turn a planet around? The first and most dramatic explanation is a story of pure chaos. It takes us back to the dawn of the solar system, a time not of serene orbits, but of cosmic bedlam. This was a shooting gallery of planetesimals and giant protoplanets, all vying for gravitational dominance in a frantic, violent dance. Worlds collided, merged, and were shattered. In this brutal epoch, the theory goes the young Venus then spinning dutifully in the same direction as its siblings suffered a blow of almost inconceivable magnitude. A rogue world, perhaps the size of Mars or even larger, careening through the inner solar system on an unstable orbit, delivered a cataclysmic glancing strike. Try to picture the scene. Not an explosion of fire and sound, for there is no air in space to carry them, but a silent, terrifyingly beautiful and destructive ballet. The impactor a shadow against the stars closing the distance. The moment of contact not a simple crash, but a merging of worlds. Trillions of tons of rock and iron vaporized in an instant, blasting a plume of incandescent plasma far out into space. The surface of Venus would have turned into a global ocean of magma, its very crust liquefied by the sheer kinetic energy released. Shockwaves not of sound but of compressed rock would have reverberated through the planet's core, ringing it like a colossal bell. But most importantly, the impact was not head-on. It was a sideswipe, a cosmic billiards shot of epic proportions. This off-center collision would have imparted a titanic rotational force, a massive wrench of angular momentum. It was enough energy not just to halt Venus's original spin, but to overwhelm it completely, sending the entire planet reeling in the opposite direction. It is a terrifyingly elegant solution, a single brutal event that could rewrite a world's destiny, forever marking it as different. It fits perfectly with our understanding of the solar system's violent youth, a time when such planetary smash-ups were not uncommon. The same kind of impact, after all, is what we believe blasted the material from a young Earth to form our own moon. Yet as with all great mysteries, the simplest answer is rarely the whole story. If such a devastating collision occurred, it should have left Clue's cosmic fingerprints at the scene of the crime. A blow of that magnitude would have likely shattered the impactor, and perhaps even a significant portion of Venus's mantle, creating a vast ring of debris around the planet. Over time, this debris would have coalesced to form a moon or several moons. But Venus is solitary. It has no natural satellite. Where did all that material go? Furthermore, a world-altering impact should have left a scar on its orbit, knocking it into a more elliptical, eccentric path around the Sun. But Venus's orbit is the most circular of any planet in our solar system, a path of almost perfect serene regularity. The evidence for a chaotic past seems to have been wiped clean. It's as if a murderer has not only hidden the body, but has also managed to scrub the entire crime scene, leaving behind an unnerving, pristine silence. The giant impact theory, for all its dramatic power, leaves us with nagging, persistent questions. Could there be another way, a less violent but perhaps even more uncanny process that could slowly, inexorably turn a world on its head? The alternative is a story not of a single moment of trauma, but of a subtle cosmic struggle, waged over billions of years. It's a tale where the main characters are not colliding worlds, but the immense, relentless forces of gravity and friction, acting upon Venus's most defining feature, its atmosphere. As we discovered earlier, the Venusian atmosphere is a monster. A crushing heavyweight blanket of carbon dioxide 90 times thicker than our own, it is less a layer of gas and more a planetary ocean of air. This atmosphere is so massive that it contains a significant portion of the planet's total angular momentum. It is a dynamic, powerful part of the world, not just a passive shroud. And this is where the story begins. The theory posits that Venus was born spinning normally just like Earth. But as the runaway greenhouse effect took hold, its atmosphere thickened, becoming the super-dense fluid we see today. Now enter the Sun. Its immense gravity pulls not just on the planet's solid body, but on this thick, heavy atmosphere, creating an atmospheric tide. It's similar to how our moon pulls on Earth's oceans, creating the familiar ebb and flow of our seas. On Venus, the Sun's gravity creates a massive bulge in the atmosphere, a permanent tidal wave of gas that wants to stay pointed towards the Sun. As the solid planet tried to rotate beneath this gaseous bulge, a tremendous friction was generated. Imagine trying to spin a ball that's submerged in thick honey. The drag is immense. This atmospheric tide constantly pulling against the planet's rotation acted as a gigantic planetary scale brake. For eons, this relentless torque waged a silent war against Venus's primordial spin. It was a whisper of a force, but it was constant, a celestial water torture that never ever ceased. Millennium by millennium, the planet's rotation slowed. The day grew longer, the spin became more sluggish, like a gyroscope beginning to wobble as its energy bleeds away. Simultaneously, another even more subtle force was at play, friction, between the planet's liquid core and its solid mantle. Just as the atmosphere was dragging on the surface, the core and mantle were rubbing against each other, dissipating rotational energy as heat within the planet's interior. These two processes, the atmospheric solar tide from above and the core mantle friction from within, worked in concert. They were a pincer movement of cosmic forces squeezing the spin out of Venus over geological time. After billions of years of this inexorable braking, the planet's rotation would have slowed to a complete standstill. For a time, Venus may have been a tidally locked world, one side perpetually facing the sun, the other frozen in eternal night. But the forces did not stop there. The atmospheric tide, this great engine of change, kept pulling. With the forward momentum gone, the torque began to act in reverse. It was a push ever so gentle in the opposite direction. Slowly, agonizingly, the great planetary machine began to turn the other way. What had once been a brake became an engine. The planet began to spin backwards, settling into the strange, languid retrograde rotation we observe today. This theory is far less dramatic than a celestial collision, but in many ways it is more compelling. It doesn't require us to look for missing moons or explain away a perfect orbit. Instead, it elegantly connects the planet's two greatest oddities, its hellish runaway greenhouse atmosphere and its backward spin. It suggests that one is the direct cause of the other. Venus isn't spinning backwards in spite of its atmosphere, it's spinning backwards because of it. The very feature that makes the planet a vision of hell is also the one that turned it into a cosmic anomaly. It is a profound and chilling thought that a planet's own climate left to run amok can become powerful enough to physically reverse its world. It paints a picture of Venus not as a victim of external violence, but as a world that through its own internal atmospheric processes fundamentally remade itself. But this grand, slow-motion ballet of atmospheric tides has given rise to something even more immediate, more violent, and more visually stunning. As we have peered deeper into that sulphurous veil, we have discovered that the story of Venus's rotation is really two stories. There is the tale of the solid globe, the rocky planet beneath the clouds, which turns so slowly that a human could easily outwalk it at the equator. And then there is the tale of the atmosphere itself, and that is a story not of slowness but of unimaginable speed. High in the Venusian sky at the cloud top some 70 kilometers up, the atmosphere refuses to obey the planet's leisurely pace. It screams around the world in the same retrograde direction, but it does so with ferocious, terrifying velocity. While the surface takes 243 Earth days to make one turn, these upper-level clouds complete a full circuit in just 4 days. This is atmospheric superrotation, and it is perhaps the greatest storm in the solar system. It is not a localized cyclone like Jupiter's Great Red Spot, or a terrestrial hurricane that lasts for a few weeks. It is a permanent planet-encircling vortex of wind. Imagine a global jet stream not thousands of miles long, but wrapping around the entire circumference of a world, with winds consistently blowing at over 360 kilometers per hour. It is a river of sulfuric acid cloud wider than a continent flowing at the speed of a bullet train forever. From space probes have watched this colossal weather system evolve. We see vast Y-shaped patterns in the clouds, signatures of planetary scale waves propagating through the atmosphere. We see spiraling vortices over the poles like twin cosmic drains where the global atmospheric ocean plunges downwards. This is a fluid dynamic system operating on a scale that dwarfs anything on Earth. It is a single, unified perpetual storm that is the planet's weather. This discovery transforms our understanding of Venus yet again. The planet is not a static, lazy spinner. It is a world of radical contrasts, a system profoundly and violently decoupled. The solid, rocky planet is the slow sleeping anchor, while the atmosphere above is a celestial blowtorch, a raging independent engine. and it forces us to ask a new, more urgent question. We have been trying to understand how the atmosphere changed the planet's spin, but what if we have it backwards? What if the incredible energy of this super-rotating storm is what is maintaining the planet's bizarre rotation today? The atmosphere moving so much faster than the ground must be exerting a phenomenal amount of friction on the surface. It is constantly trying to drag the solid planet along with it. Could it be that the relationship goes both ways, that the slow spin created the conditions for the super-rotation to begin, and now the super-rotation has become a self-sustaining engine, a vast flywheel of wind that holds the planet in its current state? We have moved from a historical mystery about a past collision or a slow decline to a dynamic present-day puzzle. The storm itself is no longer just a feature of Venus. It may be the very key to its fundamental nature. It is a force of nature so powerful it has become a geological agent, a storm beyond imagination, that has seized control of its world, dictating the length of its day and the direction of its spin. To truly comprehend Venus, we must now descend into that maelstrom. We must dissect that 4-day hurricane and understand the engine that drives a planet backwards. This colossal planet-wide hurricane, this super-rotation we have just witnessed, is not a storm in the sky. It is the sky. And it is merely the engine's roar, the overture to an atmospheric opera of unimaginable violence and exquisite strangeness. To truly comprehend the forces at work on Venus, we must now journey from this global perspective and plunge into the specific localized maelstroms that this atmospheric superpower generates. We must descend into the tempests that rage within the tempest, where the laws of meteorology are not just broken, but rewritten in a language of sulfuric acid and crushing pressure. Here in the churning depths of the Cytherean atmosphere, we find phenomena that challenge our very definition of weather, forcing us to confront the fact that a sky can be far more than just a canopy of air. It can be a chemical reactor, an electrical generator, and a geological force all at once. Our first stop on this descent is the planet's poles regions that on any normal world would be bastions of frigid calm. On Venus, they are anything but. Here the relentless high-speed winds of the super-rotation, unable to continue their equatorial journey, are forced into a desperate spiralling collapse. They bank and turn, piling into one another, with unimaginable kinetic energy, creating a vast permanent feature that dwarfs any storm system on Earth. Gazing down from orbit through specialized infrared filters that can pierce the upper haze, you would see it a colossal cyclonic structure, a swirling vortex larger than most terrestrial continents, a permanent atmospheric drain plunging deep into the cloud decks. But as we look closer, a profound and unsettling detail emerges. It is not one vortex, it is two. Locked in a mesmerizing, hypnotic dance, two distinct storm centers, two eyes revolve around a common shifting center. This is the Great Polar Dipole, the double vortex of Venus, a meteorological feature that has no direct parallel anywhere in our solar system. On Earth, our polar vortex is a singular, often ragged entity, a seasonal beast that strengthens and weakens with the passage of winter. It is a consequence of temperature gradients. The Venusian vortices, however, are different. They are permanent fixtures, gravitational gyroscopes carved into the very fabric of the atmosphere, sculpted not by temperature alone, but by the raw mechanical power of the super-rotation. Imagine two colossal whirlpools, each hundreds of miles across, spinning in a tight gravitational embrace, dragging the surrounding cloudscape down into a deep, warm abyss at the heart of the cyclone. Data from the European Space Agency's Venus Express orbiter gave us our most intimate look at this bizarre structure. It revealed a system of bewildering complexity. The S-shaped filament of clouds that separates the two eyes is a region of intense shear, where winds moving in different directions grind against each other. The core of the vortex, plunging some 20 kilometers down through the cloud layers, is paradoxically warmer than its surroundings, a pocket of compressed descending gas heated by its own fall. The dynamics are so chaotic, the shapes so fluid and unpredictable, that computer models still struggle to replicate its intricate deadly ballet. Why two eyes instead of one? What forces maintain this delicate yet violent balance against the crushing pressure to merge into a single more stable system? The answers are still buried deep within the clouds, whispered in the language of fluid dynamics, operating under conditions we can barely simulate. This twin-eyed monster at the top and bottom of the world is a constant, stark reminder that we are dealing with a completely alien weather engine, one whose fundamental operating principles remain profoundly mysterious. But the violence of Venus is not merely mechanical. It is also electrical. For centuries, the idea of lightning on Venus was a tantalizing yet unproven hypothesis. The thick sulphurous clouds certainly seemed a perfect crucible for generating immense static charge, but early probes sent conflicting signals. Some detected whispers of electromagnetic interference, others found nothing but an unnerving quiet. The mystery persisted for decades, a scientific puzzle box. How could a world with such a dynamic atmosphere, a veritable planetary-scale chemical factory, not produce lightning? The answer we now know is that it does, and it does so on a scale that is both terrifying and beautiful. It is not the kind of lightning you're used to. On Earth, lightning is a spectacle born of water and ice. Colliding ice crystals and supercooled water droplets within towering cumulonimbus clouds strip electrons from one another, creating the immense charge separation that is ultimately neutralized by a blinding flash of plasma. It is a process fundamentally tied to the physics of H2O. On Venus, there is virtually no water in the atmosphere. The charge separation here is born from something far more corrosive and alien droplets of concentrated sulfuric acid. The constant violent churning within the Venusian cloud layers the friction between untold trillions of acid droplets and perhaps some unknown aerosol particles, generates an electrical potential that constantly builds and discharges. This isn't a storm that comes and goes. The lightning on Venus appears to be continuous, a never-ending electrical crackle woven into the atmospheric fabric itself. The Akatsuki probe from Japan, using a high-speed lightning camera, has given us glimpses of these flashes, confirming what radio antennas had long suspected. They are not grand cloud-to-ground bolts, because the lower atmosphere is too thick and dense for a spark to easily traverse it. Instead, we see vast intracloud displays, enormous sheet lightning, that illuminates the toxic cloud decks from within, like ghostly flashbulbs firing in a perpetual silent rave. These are not isolated events. They are happening somewhere on the planet all the time. Imagine floating in that thick yellow haze. You would not be waiting for a storm to roll in. You would be living inside of it. The sky would be in a constant state of electrical fury, discharging its energy not in singular dramatic thunderclaps, but in a relentless planet-wide fusillade. This unending acidic fire is more than just a light show. It is a critical component of the planet's chemical engine. Each bolt of lightning is a celestial blowtorch, its immense energy momentarily tearing apart the complex molecules in the atmosphere. Carbon dioxide, sulfur dioxide, and nitrogen are ripped into their constituent atoms, which then furiously recombine into new exotic compounds. This process, known as atmospheric electrolysis, is a key driver of Venus's bizarre chemistry, helping to maintain the delicate balance of gases that feed the runaway greenhouse effect. The lightning is not just a symptom of the atmospheric conditions, it is an active participant, a catalyst in the alchemical furnace of the sky, ensuring the planet's toxic brew is continuously stirred and replenished. Every flicker and flash we detect is another testament to the raw, untamable energy that permeates every cubic meter of this world's atmosphere. As we move deeper from the electrical fury of the clouds toward the crushing reality of the surface, we encounter a phenomenon so bizarre, so seemingly impossible that it sounds like a fantasy. It is a form of precipitation that exists nowhere else, a weather event born from the unique convergence of extreme temperature and extreme pressure. It is the eerie spectacle of metal snow. The first clues came not from landers but from orbiters. In the 1990s, the Magellan spacecraft used its powerful radar to map the Venusian surface in stunning detail. As the images came back, scientists noticed something peculiar. The highest mountain peaks on Venus' soaring highlands, like the Maxwell Montes, were strangely bright on radar. They reflected radio waves with an astonishing, almost metallic efficiency, standing out like ghostly white caps against the darker, less reflective lowlands. For a time, this was a profound enigma. What could possibly coat the mountaintops of a world where the surface temperature is hot enough to melt? Lead water ice was an impossibility. It would have boiled away into space billions of years ago. Some kind of unusual rock, perhaps. But the effect was too uniform, too perfectly correlated with a specific altitude. The solution, when it was pieced together, was more wondrous and more alien than anyone had imagined. The highlands of Venus are not covered in ice, but in a frost of condensed heavy metals. The process begins in the scorching, hellish lowlands. At over 460 degrees Celsius, the pressure and heat are so intense that certain metallic minerals on the surface compounds like lead sulfide and bismuth. Sulfide don't just melt, they vaporize. They sublimate directly into a metallic gas which then mixes with the dense carbon dioxide atmosphere. Just like water vapor on Earth, these metallic gases are carried upward by atmospheric currents and circulation patterns. As this metal-laden air rises toward the highlands, it begins to cool. Maxwell Montes, the highest mountain range on Venus, towers over 10 kilometers above the mean planetary radius. At its summit, the temperature, while still incredibly hot by our standards, is significantly cooler than in the planetary basins, perhaps a mere 380 degrees Celsius. This altitude marks a critical threshold, a cosmic snowline. Here the temperature drops just enough for the metallic vapours to reach their dew point. The lead sulfide and bismuth sulfide condense out of the atmosphere and precipitate onto the rock, forming a thin, glittering layer of metallic frost. Over eons, this process has plated the highest peaks of Venus in a shimmering, highly reflective and electrically conductive sheen. It is for all intents and purposes a snowfall of metal. You could stand on the summit of Maxwell Montes and witness a gentle perpetual flurry, not of delicate snowflakes, but of heavy toxic metallic crystals settling from the thick ochre sky. This is not just a geological curiosity. It is a fully fledged meteorological cycle, a metal cycle that mirrors our own planet's water cycle, but with materials drawn from a blacksmith's forge rather than a pristine spring. The existence of this cycle demonstrates just how deeply intertwined the geology and atmosphere of Venus are with the ground, itself breathing its substance into the sky, only to have it returned as a bizarre industrial precipitation. These dramatic phenomena, the twin vortices, the perpetual lightning, the metal snow, are the grand visible manifestations of a far deeper and more complex system. They are the cresting waves on the surface of a turbulent ocean of energy and chemistry. To truly grasp the nature of Venus's atmosphere, we have to look beneath these waves into the unseen engine that drives it all. We must ask the most fundamental question: where does all this energy come from? The Sun, of course, is the primary source bombarding the planet with intense radiation. But unlike Earth, which reflects a significant portion of this energy back into space, Venus has trapped it. The thick blanket of carbon dioxide and sulfur dioxide has created the most efficient greenhouse in the solar system, a one-way thermal gate where heat can enter but cannot easily leave. This trapped energy fuels everything. It is the power source for the superrotation and the heat that drives the polar vortices and the engine of the chemical cycles. At the heart of this engine is sulfur. On Earth, sulfur is a minor player in our atmosphere. On Venus, it is a star. The entire weather system is built around a vast planet-wide sulfur cycle. High in the atmosphere above the main cloud deck, intense ultraviolet radiation from the sun strikes molecules of sulfur dioxide, breaking them apart in a process called photodissociation. These reactive sulfur atoms then combine with the trace amounts of water vapor to form droplets of sulfuric acid, the very substance that makes up the opaque yellow clouds. These acid clouds are not static, they are constantly raining down. But this is not rain as we know it. The droplets of sulfuric acid fall from the upper cloud layers, but they never ever reach the ground. The temperature in the lower atmosphere is so extreme that long before a droplet could complete its journey, it evaporates in midair. This phenomenon, known as virga, creates a perpetual ghostly shower that exists only in the sky, a rain that is born and dies without ever touching the surface. The evaporated molecules are then broken down again by the heat, releasing their sulfur dioxide to be swept back up into the upper atmosphere, by convection currents, where the cycle can begin anew. The entire cloud system is in a state of dynamic equilibrium, a planetary-scale chemical factory that is continuously manufacturing, raining and recycling its own acidic components, with the unending lightning acting as a chaotic variable, a wild card constantly altering the chemical equations. And yet even with this understanding, a profound mystery lies at the very heart of the Venusian energy budget. When we measure the amount of solar energy that Venus absorbs, we find a discrepancy. The clouds, while reflective, are also absorbing a colossal amount of ultraviolet light, far more than can be explained by the known gases like carbon dioxide and sulfur dioxide. Something else is in there, something hidden within the acid haze, a mysterious substance that is drinking in almost half of the solar energy the planet receives. Scientists have grimly dubbed it the unknown UV absorber. Its identity is one of the greatest unsolved puzzles in planetary science. For decades, we have tried to determine what it could be. Is it a different form of sulfur? Perhaps long chains of sulfur atoms called allotropes that have unique absorptive properties? Could it be ferric chloride, another chemical suspected to exist in the clouds? Some have even made the highly speculative and deeply tantalizing suggestion that this absorption could be caused by microorganisms, a form of aerial biosphere floating in the one relatively temperate layer of the Venusian atmosphere, using the UV light for some form of photosynthesis. We simply do not know. But what we do know is that whatever this substance is, it is not a minor component. It is a critical driver of the entire atmospheric system. The energy it captures is what heats the upper cloud deck, creating the thermal gradients that help power the superrotation. Without this mysterious absorber, the winds might be slower, the storms less fierce, the entire planet a fundamentally different place. We are left then with a portrait of a world governed by forces that are both majestically powerful and subtly elusive. We see the grand structures of the polar vortices, yet we cannot fully model their dance. We see the flash of lightning, but we are still cataloguing the exotic chemicals it forges. We understand the theory behind the metal snow, but we have never seen it fall. And at the very heart of the engine that drives it all, there is a ghost, a mysterious energy-absorbing entity whose nature remains a complete unknown. The atmosphere of Venus is not just a collection of weather phenomena, it is a singular unified entity, a complex system where physics, chemistry and geology are fused together. It is a puzzle box of colossal proportions, and cracking it is not just about understanding another planet, it's about understanding the very limits of how a world can evolve. How could a planet born as Earth's twin have developed an atmosphere so profoundly, so violently different from our own? To find the answer, we must peel back these layers of storm and chemistry and look deeper into the planet's ancient past, to a time when two sisters stood at a fork in the cosmic road and took catastrophically different paths. And so the brutal mechanics of this world now laid bare demand a final terrifying synthesis. We have charted the currents of its blistering high-speed winds. We have mapped the scars of its unceasing volcanic fury. We have felt the ghost of its backward spin, a planetary gyroscope that dictates the sluggish passage of its scorching days. Each piece of the puzzle on its own is a testament to an extreme, but woven together they reveal something far more profound. They paint a portrait of a planet caught in a self-perpetuating cycle, a feedback loop of immense power that locks it in its hellish state. The thick carbon dioxide-rich atmosphere born of eons of eruptions acts as both an insulator and a colossal engine. It traps the sun's heat with suffocating efficiency, driving surface temperatures high enough to melt lead. This same thermal energy churning in the upper cloud decks fuels the superrotation, the planet-girdling atmospheric river that races 60 times faster than the world turning beneath it. That sluggish rotation, in turn, allows the atmosphere to build this incredible momentum unchecked by the rapid Coriolis forces that break up weather systems into smaller storms here on Earth. It's a perfect malevolent machine where the geology feeds the atmosphere, and the atmosphere's motion is shaped by the planet's strange spin. Everything we have witnessed, from the crushing pressure at the surface to the sulfuric acid haze, is interconnected. This is not a collection of independent phenomena. It is a single integrated system of planetary torment. But this perfect machine, so stable in its hostility today, begs the most important question of all. Was it always this way? Could a world so exquisitely, so completely inhospitable have begun its life alongside our own blue Earth as a kindred spirit? The answer, whispered from the very chemical makeup of its atmosphere, is the most haunting revelation in our exploration of the solar system. To find it, we must look for the ghost of an element. We must search for the spectral signature of water. In the wispy upper reaches of the Venusian clouds, where trace amounts of water vapour still cling to existence, our probes have detected something incredibly strange. They have found an astonishing abundance of a heavier form of hydrogen, an isotope known as deuterium. Here on Earth, for every 1 million hydrogen atoms in our oceans, only about 156 are deuterium. On Venus, that ratio is 100 times higher. This isn't just a minor chemical curiosity. It is a smoking gun. It is a planetary post-mortem written in the language of atoms. Imagine the sun's unforgiving ultraviolet radiation shining on a vast ocean. This high-energy light acts like a subatomic scalpel, splitting water molecules H2O into their component parts hydrogen and oxygen. Standard hydrogen, being the lightest element in the universe, would rapidly escape the planet's gravitational pull, bleeding out into the vacuum of space over millions of years. Deuterium, however, burdened with an extra neutron, is twice as heavy. It is more sluggish, more firmly anchored by gravity, and far more likely to be left behind. The staggering overabundance of deuterium on Venus today can only mean one thing. It is the heavy dregs left over from a truly colossal quantity of water that has since been lost to space. When we run the models calculating how much water had to be brutally stripped away to leave this specific isotopic fingerprint, the numbers are almost beyond belief. They point to a Venus that once possessed enough water to cover its entire surface in a global ocean, an ocean potentially hundreds of meters, perhaps even kilometers deep. This isn't science fiction. This is the direct logical conclusion from the evidence at hand. Venus the Inferno was very likely once a blue world, a water world. Suddenly other enigmatic features of the Venusian surface snap into sharper focus. The ancient highly deformed highland regions known as Tisserie, with their complex patterns of ridges and grooves, look suspiciously like continents on Earth. Some scientists now believe these might be the remnants of an ancient crust formed in the presence of abundant water, before the planet's surface was paved over by massive lava flows. For a time, perhaps for 1 billion years or even more, the history of our two planets may have run in parallel. Two similar worlds born from the same protoplanetary disk, orbiting the same young star, both draped in liquid water. Imagine that primordial Venus. Picture sunlight filtering through a thinner nitrogen-rich atmosphere, glinting off the waves of a planet-wide sea. Perhaps clouds of water vapour scudded across its skies, casting shadows on volcanic islands rising from the blue. Under such conditions, the building blocks of life delivered by comets and forged in hydrothermal vents could have followed the same path they did here on our own world. We may never know if life ever began on this ancient Venus, but for a tantalizingly long chapter of cosmic history, it almost certainly had the chance. It possessed all the necessary ingredients. It was a garden waiting to bloom. What followed was not a single violent event, but a slow, insidious unravelling. A cataclysm in slow motion. The culprit was the one thing the planet could not escape its star. Our sun, like all stars of its kind, has been gradually brightening since its birth 4.5 billion years ago. In its youth, it was about 30% dimmer than it is today. As it aged, its luminosity steadily increased, pouring ever more radiant energy out into the solar system. For Earth located farther out, this gradual warming was gentle enough for our planet's complex climate systems to regulate and adapt. For Venus orbiting perilously closer, it was a death sentence. There came a tipping point, a moment when the incoming solar energy became too great for the planet to radiate back into space. The surface temperatures began to climb not by degrees but by leaps. As the oceans warmed, they evaporated more and more water vapour into the atmosphere. But water vapour is itself a powerful greenhouse gas. The more water vapour in the air, the more heat was trapped, which in turn caused the oceans to evaporate even faster. This was the beginning of the runaway greenhouse effect, a positive feedback loop from which there was no return. It was a one-way street in planetary evolution. The process would have been terrifying to behold. The oceans, once placid and life-giving, would have begun to boil. First in the equatorial regions, then spreading towards the poles, the planet's surface would have transformed into a seething cauldron. A dense, suffocating steam atmosphere would have enveloped the globe, raising the pressure to unimaginable levels. The sky would have ceased to be blue, turning into a murky, oppressive shroud. As the last of the oceans violently boiled away, the true catastrophe was only just beginning. With no water left to weather them, the rocks themselves began to bake. Carbon locked away for eons in carbonate minerals on the seafloor was cooked out by the extreme heat and released into the atmosphere as immense quantities of carbon dioxide. This deluge of CO2 supercharged the greenhouse effect, ratcheting the temperature up from the boiling point of water to the 900 degrees Fahrenheit we see today. Simultaneously with the oceans gone, the planet's geological engine was fundamentally altered. On Earth, water acts as a lubricant for plate tectonics, allowing crustal plates to slide and subduct, recycling the surface. Without water, the Venusian crust may have seized up, becoming a single stagnant lid. Heat from the planet's core, unable to escape efficiently, built up beneath this lid until it burst forth in planet-wide volcanic convulsions, releasing even more CO2 and sulfur compounds. The world we see today, desiccated, acid-drenched and crushed under an atmosphere 90 times heavier than our own, is the end result of this cascade failure. It is a planet that has been sterilized, fossilized, and then embalmed in its own toxic atmosphere. The ghost of its ocean is now just a chemical stain in the clouds, a final faint cry from a paradise that was utterly and completely lost. And in this planetary post-mortem we find the most profound and unsettling lesson Venus has to offer. It holds up a cosmic mirror to our own world. The physics that destroyed Venus are the same physics that operate here. The greenhouse effect is not theoretical. Its most extreme expression is orbiting the Sun right next to us. Of course the circumstances are different. Earth is farther from the Sun. Our planet never reached that initial irreversible tipping point. But the story of Venus is a chilling demonstration of how a planet's climate, once destabilized, can run away to an unimaginable extreme. It proves that habitability is not a permanent state of being. It is a delicate, ephemeral balance easily broken. When we pump carbon dioxide into our own atmosphere, we're not turning Earth into Venus. But we're nudging our world's thermostat with the very same mechanism that killed our planetary twin. Venus serves as the ultimate cautionary tale, a vision of a potential future, not for Earth as a whole, but for the fundamental stability we take for granted. It teaches us that a planet's climate is not a gentle, self-correcting system. Push it too far, and it will not gently return. It will find a new, terrifying equilibrium. This stark lesson extends far beyond our own solar system. It fundamentally reshapes our search for life in the universe. For decades, astronomers have spoken of the habitable zone, that temperate band around a star where liquid water could in theory exist on a planet's surface. We have pointed our most powerful telescopes at this zone, dreaming of finding another Earth. But Venus complicates this simple picture. It orbits just inside the inner edge of our Sun's modern habitable zone, yet it is a furnace. Its history suggests that the true habitable zone is not a fixed address. It is a dynamic, shifting boundary, and its inner edge is a treacherous place. A young dim star might allow a close-in planet to flourish for 1 billion years, only for that same star's inevitable brightening to trigger a runaway greenhouse effect and extinguish any life that had begun. When we now look out into the cosmos and detect an Earth-sized planet orbiting in what seems to be a habitable zone, we face a new ambiguity. Are we seeing a thriving ocean-rich world teeming with potential? Or are we seeing a planet in its final, Venus-like death? Throes, its oceans boiling away into a thick, steamy atmosphere. From a distance of dozens of light-years, the two can look deceptively similar. The light filtering through their atmospheres might at first glance be hard to distinguish. Venus provides us with the essential ground truth. It is our local laboratory for understanding planetary failure. By studying its atmospheric composition, its cloud chemistry, and the spectral signatures of its runaway state, we are building a field guide for telling the difference between a living world and a dead one. Without the terrifying example of Venus, we would be flying blind, prone to a dangerous optimism, potentially misinterpreting a planetary death cry as a sign of life. It is the Rosetta Stone for deciphering the light from these distant worlds, allowing us to discern the subtle clues that separate a paradise from a purgatory. This is the ultimate dichotomy of our sister world. Venus is both a profound warning and an invaluable scientific treasure. It is a story of loss on an almost unimaginable scale, the tale of a world that had every chance at becoming another Earth, only to take a catastrophic turn. That single divergence billions of years ago sent our two worlds down two completely different evolutionary paths. Earth's path led to plate tectonics, stable oceans, and a climate that allowed for the flourishing of complex life. Venus's path led to a stagnant crust, boiled-off oceans, and a self-perpetuating atmospheric furnace. They are two outcomes from nearly identical starting conditions, a natural experiment of cosmic proportions. Understanding precisely what factors led to this schism, the planet's slower rotation, its lack of a magnetic field, subtle differences in its initial composition, is now one of the most critical goals in all of planetary science. Because in answering that question, we answer a much deeper one. Which of these two paths is more common in the universe? Is Earth's enduring stability the rule, or is it the fragile exception? Is the galaxy filled with thriving blue worlds, or is it littered with the silent, scorched remains of planets that, like Venus, lost their way? The answer is waiting for us locked in the ancient rocks and acidic clouds of the world next door. And it compels us with a new and powerful urgency to go back. We must return to this veiled inferno not just to understand our past, but to secure our future and finally grasp our true place among the stars. From a shimmering point of light in our twilight sky, an object of myth and romantic speculation, Venus has been transformed in our minds. We have journeyed with courageous probes and tireless scientists through a century of discovery, peeling back its layers of mystery one by one. The story we began with a tale of a potential tropical paradise, our celestial twin veiled in gentle clouds, has dissolved into a far more formidable and fascinating reality. We have replaced the fantasy of a sister world with the hard-won knowledge of a planetary inferno, a vision of what could have been and a stark warning of what can be. Our journey has taken us from the first tantalizing whispers of radio telescopes, which hinted at an impossible heat, to the heroic final transmissions of the Venera landers crushed and melted on a surface we could barely comprehend. You have stood with us on the precipice of imagination, staring into the crushing depths of an atmosphere 90 times thicker than our own. You have felt the searing touch of its lead-melting surface temperature, a global constant with no relief from day to night. You have witnessed the surreal spectacle of sulfuric acid clouds racing around the planet in a perpetual super-rotation, a weather system divorced from the slow, ponderous turn of the world beneath. We have unravelled the physics of its runaway greenhouse effect, the ultimate cautionary tale written on a planetary scale. We have grappled with the profound enigma of its retrograde spin, a world turning backwards against the cosmic current its day longer than its year. Each discovery, each piece of data painfully acquired has not diminished Venus, but has instead magnified its power, its strangeness, and its profound importance. It is no longer a simple twin to Earth, but something far more valuable, a cosmic mirror reflecting a different path taken. Venus is the control experiment of planetary formation, a laboratory where we can test the very limits of atmospheric science and geology. When we build models to understand climate change on our own world, we push them to their breaking point against the data from Venus. If a model can accurately predict the hellscape of our neighbour, only then can we truly trust its predictions for the delicate balance of Earth. Every hurricane that spins across our oceans, every volcano that reshapes our landscapes, is a whisper of the forces that roar unchecked across the second planet. Venus shows us nature's raw power, untamed by liquid water oceans, untempered by life, a planet operating at the extreme edge of possibility. This understanding extends far beyond the confines of our own solar system, reaching out to the countless stars glittering in the cosmic dark. As we scan the skies for exoplanets for other Earths, we are finding just as many, if not more, worlds that may well be other Venuses. Planets huddled too close to their parent stars, caught in the same gravitational and thermal trap that sealed our neighbour's fate. The data we gather from Venus is not merely for our own curiosity. It is the vital ground truth, the calibration key for interpreting the faint light from worlds trillions of miles away. It helps us define the Venus zone, that perilous region around a star where a planet's atmosphere is destined to boil away its oceans and suffocate its surface. By understanding Venus, we learn how to separate the truly habitable worlds from the magnificent but lethal impostors. Yet for all we have learned, for all the veils we have pierced, the planet of love still guards its most profound secrets with a furious jealousy. The story is far from over. In fact, we stand at the threshold of a new golden age of Venus exploration, a time when lingering questions that have haunted scientists for decades may finally be answered. These are not trivial details. They are the fundamental chapters of Venus's biography that remain unwritten. Chief among them is the ghost of its ancient ocean. We see the chemical fingerprints in its atmosphere, the elevated ratios of deuterium to hydrogen, a tantalizing clue that vast quantities of water once existed here. But when did it vanish? Was it lost in a sudden violent cataclysm, or did it slowly bleed away into space over 1 billion years? What did the planet look like during this lost epoch? For a time, was Venus truly the temperate water world twin of Earth that we once dreamed it to be? Deep within its geology lies another profound mystery. The surface we see mapped by Magellan's radar appears bizarrely young, as if the entire planet was catastrophically repaved in a global volcanic event some 500 million years ago. Imagine Earth with all its continents, mountain ranges, and ancient craters being completely wiped clean and covered in fresh lava. What kind of unimaginable tectonic process could do such a thing? Did it happen all at once in a geological instant, or was it a series of massive overlapping eruptions? And perhaps the most electrifying question of all, is it still happening? Are there active volcanoes on Venus today? We have seen hints in the data, transient hotspots that flicker and fade, strange bursts of sulfur dioxide in the upper atmosphere like puffs of smoke from a hidden fire. Confirming active volcanism on Venus would transform it from a static historical artifact into a living, breathing geologic entity. To answer these questions, to write these missing chapters, we cannot rely on the technologies of the past. We must return not with singular fleeting glimpses, but with a sustained systematic campaign of observation and descent. Humanity is preparing to do just that. A new fleet of robotic explorers is being readied, designed with the benefit of all our previous knowledge, engineered to withstand the planet's fury, and equipped with instruments of unprecedented sophistication. They represent our commitment to finally understanding this enigmatic world, to solving the grand puzzles it still presents. 2 of these missions, poised to launch within the next decade, promise to revolutionize our vision of Venus much as their predecessors did generations ago. They are Veritas and Da Vinci, twin pillars of a new era. Veritas, the Venus Emissivity Radio Science, INSAR Topography and Spectroscopy mission, will be our master geologist in orbit. It is designed to create a global high-resolution 3-dimensional map of the Venusian surface, a vision of startling clarity that will surpass the pioneering but aged maps of Magellan by orders of magnitude. Veritas is not just a map maker. It is a detective searching for the planet's geologic pulse. Using a technique called interferometric synthetic aperture radar, it will scan the surface for tiny changes between its orbital passes, looking for ground deformation as small as a few centimeters. This is the holy grail of Venusian geology, the ability to spot the subtle swelling of a magma chamber miles below the surface, the sagging of a volcanic flank after an eruption, or the telltale signs of a Venus quake. For the first time, we may be able to create a global map of active volcanic zones, transforming our suspicions into certainties. Its powerful radar will peel back the clouds permanently, allowing us to see the face of Venus in breathtaking detail. We will finally get a clear view of the mysterious Tesserae, those ancient fractured highlands that are thought to be the oldest remnants of Venus's original crust. Are they continental plates, like those on Earth frozen in time? Are they composed of granite-like rocks that could only have formed in the presence of abundant water? Veritas will analyze their composition from orbit, using infrared spectroscopy to identify their mineral makeup. the answer could tell us definitively whether a water-rich past is a scientific fact or a persistent fiction. The mission will also chart the planet's gravitational field with exquisite precision, allowing us to probe its interior structure from the thickness of its crust to the nature of its core. Veritas will give us the planet's complete anatomy from its molten heart to its weathered skin. But to truly understand Venus, we cannot remain in orbit. We must plunge into the belly of the beast. That is the daring task of the second mission Da Vinci, the deep atmosphere, Venus investigation of noble gases, chemistry and imaging. Da Vinci is a direct descendant of the heroic Soviet Venera probes, but equipped with 21st century technology. It will carry a spherical probe, a robust titanium-clad vessel, designed for one purpose: to survive a 1-hour descent through hell. As it falls through the sky, it will be our ultimate atmospheric laboratory, a sniffer and a sampler on a journey through the unknown. For 63 minutes it will taste the air, analysing its chemistry with a precision we have never before achieved. Its primary targets are the noble gases neon, argon, krypton, xenon, the silent storytellers of planetary history. These gases are chemically inert. They do not react or change over billions of years. The specific blend of their isotopes acts as a pristine fingerprint of the planet's formation and its subsequent evolution. By measuring them precisely, Da Vinci can effectively open a time capsule, allowing us to read the story of how Venus acquired its atmosphere. Did it form from the same building blocks as Earth, or did it have a more exotic origin? How much water did it truly start with? The probe's instruments will dissect the atmosphere layer by layer, measuring trace gases and chemical cycles, helping us understand the complex machinery that drives the super-rotating winds and maintains the sulfuric acid clouds. It will paint the first complete picture of the atmosphere as a single interconnected system from the cloud tops down to the scorching depths. And in its final moments, as the probe descends through the last, thickest layers of the murk, it will do something no mission has successfully done in over 40 years. It will look down. Through a special window made of sapphire resistant to the incredible heat and pressure, a camera will take the first ever high-resolution images of the enigmatic tesserae terrain from below the clouds. We will see these ancient crumpled landscapes as a lander would, watching the ground rush up to meet us. We will discern features as small as a yard across, seeing the textures, the rock types, the erosional patterns of a landscape that may be over 1 billion years old. These images will be our first ground truth, a vital link between the global orbital view from Veritas and the reality of the surface itself. They will be the last testament of the Da Vinci probe before it succumbs to the planet it was sent to understand, a final poignant postcard from another world. Together, these missions are not just an exploration, they are an interrogation. They will work in concert, the orbital perspective of Veritas, providing the global context for the in situ measurements of Da Vinci. One gives us the grand geologic map, the other provides the chemical and historical footnotes. The data they return will feed a new generation of scientific inquiry, sparking new theories and rewriting textbooks. We will finally move from a planet of grand theories and tantalizing hints to a world of solid data and concrete answers. The gaps in the story of the terrestrial planets will begin to close, and Venus will take its rightful place not as an anomaly, but as a crucial piece of the puzzle of how worlds like our own come to be. The journey to understand the planet spinning backwards has been one of humanity's great scientific epics. It has been a story of transcending our own terrestrial biases, of learning to see the universe not just as we wish it to be, but as it truly is. Venus teaches us that the line between a habitable paradise and an uninhabitable furnace can be terrifyingly thin. It reminds us that a planet is not a static object, but a dynamic system, with a life story full of turning points and irreversible changes. The forces that sealed Venus's fate are the same forces that operate on Earth, a constant reminder of the fragility of our own world's balance. Its hostile beauty, its violent storms, and its crushing pressure are not a failure of nature, but a different, equally valid outcome of planetary evolution. As we continue to gaze outward, seeking our place among the stars, we will carry the lessons of Venus with us. It is the silent, burning sentinel of our solar system, a monument to the immense and often terrifying power of the cosmos. Its secrets have been hard won, and many more remain locked behind its impenetrable clouds and buried beneath its volcanic plains. But we will continue to knock on its door to send our emissaries to listen for its ancient secrets. Because in its story we find a deeper understanding of our own. The quest to know Venus is and always has been part of the quest to know ourselves, and the journey as we now see is only just beginning.